Okay, I'm recording. Can you see that?
Hi everyone. I will share about a
Okay.
paper on disk-based confidence score, and also it's Amit and Daphna, and it's published on arXiv only, but it got 41 references. So the rationale of this paper is that how to determine if a result given by the neural network is confident or not. There's example that a cartoon image may be fed into a model trained by ImageNet, but give some output that is not correct. So this case is especially for classification neural network. After softmax layer, a class may be output even the probability itself is low. So how can we calculate a confidence score to indicate how confident the model is? In the above situation, the confidence score should be small, because the model is not trained for cartoon. So let me have a recap of what is CNN. The full name, convolutional neural network. So a typical CNN is usually formed by several layers of convolutional layer, and a max and average pooling, and times n times finally followed by a fully connected layer. So it's what a neural network, a CNN, a typical CNN will be, like this AlexNet. Yeah. Okay, so I'll also go. So, okay, maybe I can say that there's in the last layer, it's called a softmax layer. It will calculate, recalculate the score to output the probability of each class, and then it will choose the highest probability to be the output of this CNN. So what is called softmax. Yeah. Okay, so some related work. So there are several commonly used confidence scores before this paper. The first is called max margin. It's the maximal activation after normalization in the output layer of the network. So in easy understand way, it's just the probability of this class, the highest probability of among all the classes, and this is used as a confidence score. So like if a model is very believe that a model has a like 90% above probability, then it should be confident, right? If a class is win using a 20% probability, the confidence should be slow. Yeah, so small. So that's one way. And second one is called entropy.
I'm sorry, I have a question of the max margin. So here, according to the definitions, how the margin play a role here?
Actually, it's only a name, I believe, because yeah, maybe it can classify from 0% to 100%. It splits the whole percentage into several margins and give a confidence.
But basically, the basic idea you mentioned here is that we're just using the value of the softmax output.
Yeah. So
yeah, and you can consider the equation to calculate the softmax. It actually is a relative value. It has a relative value. So the larger the margin between the best one and the second best one, the larger the final probability.
Yeah, you can see my third confidence score is called the max margin against second. The max activity divided by second maximal activation. That's also one way, but
they're the same, right? So the information has been included here. So you can see the max margin against the second. So the margin actually means the value.
Yeah, maybe it means the value. Yeah, I'm not so sure. Yeah,
because you can see, suppose we just take the value of the softmax value. So the difference between the difference has already been there. Because the softmax is actually a relative value, the acceleration of those relative value, that is the essence of the softmax. So basically, the value itself has already contained the margin information. And so it does not need to, again, to compare with the second, because it's already being the relative value.
Actually, it need because the softmax will output something related to exponential. So by dividing the second, it's like minus minus the value in original before the softmax. So it's kind of difference between the first.
If I remember correctly, if there are two values, it's ex and ey, right? So the softmax here is going to try to let x y over ex e to x plus e to y, right?
I don't think so. I think softmax is only. Let me wrote something.
You can just you can switch back to the Wikipedia. So you can just.
I think it's something related. Okay. I can switch to Wikipedia for softmax.
Yeah. So softmax is actually a relative value. Basically, there's a relative value there. Right.
So you can see that it's not. It's actually not a soft relative value. It's like all the.
It's a relative value. It's a relative value of after perform the exponential operation.
Yeah. But the reason why it's needed to divide by a second one is that because all the so all the.
You can see the denominator are the same. The first one, the second one.
Yeah, so yes, all the denominators are same. So after we divided, so we are actually comparing with zj minus zy. So it's actually comparing z max minus the second.
Okay, so it's calculated in such a way.
Yeah, so actually it's kind of difference between the first activation and second activation. Yeah. So why is it's different between the first one.
Okay.
Okay, and I'll clean all the. So the second is the entropy. So so it's the negative entropy of classic activations in the output layer. So the lower the entropy, the higher the confidence because yeah. So okay.
Sorry, I have a question. So the entropy. So yeah, I think basically they are convey the same idea, right? Convey the same idea,
so all the related are convey the same idea. Yeah.
But they're actually using different measurement. So suppose there are two output value which are very similar. So that means the entropy will be larger.
Will be.
Will be larger. So that means that the larger the entropy, the less the confidence.
Correct. So it says the negative entropy of the activations. Okay, so some limitations is that it only considers the output of one single test data. So one idea is that what if we can utilize some of the trained data to be an indicator? So if a test data is very different from other training data, the confidence score should be lower. So that's what the idea behind this paper.
So basically, it is a measurement of the how unseen or how rare this instance is different from the training data.
Yep, correct. And so that's what I believe. What I summarized from the idea of this paper.
That makes sense.
Yep. So there's a brief idea. So there's a hypothesis is that a similar kind of image should be closed in embedding space. So what is embedding space? I will introduce later. And if we can first record the embedding space for training data, then we can use the embedding for test data to compare with the recorded embeddings to give a confidence score. So this is a brief idea of this paper. So there are three key questions to answer for this brief idea. So output of which layer should be used as embedding. Second is how the confidence score is actually calculated. And third, is the hypothesis always true?
Could you go back to the hypothesis? Yeah, I have a question of the similar. How do you mean? How do you mean the similar? How do you define?
Okay, so it means the images belongs to same class.
Okay, so it should be squeezed to. But is there possible that let me raise an example. Suppose they have two different kind of dogs.
Yeah.
One kind of dogs is more
not
like a
always
wolf. Suppose the dog is, one kind of dog is very look like a wolf, and the other dogs maybe just like a pet. You serve the pet. Those kind of dogs are very different, but they all belong to the dog. So actually, they may kind of the embedding space of them may be different, but
yeah,
then you can
so
still
correct.
classify them into
Correct.
the same class, right?
Yeah, you're correct. So I got the third question, is the hypothesis always true? So
Okay.
I'll answer this later.
Okay, so we still go back to the previous slide.
Okay.
Yes, we call. Okay, so actually you are generally to look at the embedding space.
Yes. So
okay, please go on. So then I think that's the only way to go, right? To look at the embedding space.
Yeah, that's the only way. Okay, so for now, what is embedding space? So actually, the paper mentions that we can use any upstream fully connected layers, the output of upstream fully connected layers to be the embedding space. Just need to change the related loss functions, but usually use the output of last layer before softmax to be the embedding. Because if you use previous layers, it will introduce extra nonlinear in embedding by the following fully connected layers. So usually people use the last layer before output softmax to be the embedding. So, but the paper mentions that any other upstream layers can work. Only need to change the related loss function.
So the idea is that you're going to using multiple FC layers as the indicator. So it means that you're using the embedding in multiple layers.
No, only you choose one, but after you choose one, you need to change the related loss function to change the embeddings a bit. Yeah. Okay, so but the answer of the article for this question is that it can use any upstream fully connected layers. But usually
would you
people
please
use
be more specific that if we use some previous layers, it will introduce an extra nonlinear, should be a nonlinearity, right? Should be nonlinearity in the embeddings. So why? So I think as far as we understand, the more fully connected layers we have, the more nonlinearity we will have. So why so if we're using previous layers, we are supposing to introduce less nonlinearity.
Yeah, correct. Yeah, correct. So that's the so one concern is the performance. Yeah. So the author mentioned that if you use previous layers, the performance will be not as good as using the last layers because it will introduce extra loss function and it will have some impact on the result. Yeah.
Okay, please go on.
Yeah, but this one you can just ignore this line. Yeah, but people just use yeah.
I think the idea is that if you use the previous layer, then for example, you observe for two images, this embedding space is similar, but after we go through the following FC layers, these two images are actually dissimilar at the last fully connected layer. As for the final result, we believe the last fully connected layer is more reliable, so we use the last layer, I think.
Yeah, there may also be some be one reason. Yeah.
Okay, please go on.
Okay, so next I'll introduce how the confidence score is calculated in the embedding space. So the formula looks scary, but actually the idea is quite simple. So first there's a k here. It means a hyperparameter. So it will choose k nearest neighbor in embedding space of training data for test embeddings. So we will have a test image, right? After the neural network will get an embedding. So remember that we record the embedding for all the test data, right? So we will use this this embedding to look into the database and to find this k closest point in the database. So this was k stand means. And fx means the embedding of x, like this fx. Y means the output label of y. So this one you can understand as a refined Euclidean distance in embedding space. Yeah. So
let me check. So yi equals y hat. So
no. I will introduce it. So this means among all the k train data, for those with the same label with the test data, so maybe so this will output a result as y hat. So amongst all those k train data in the database, some of them may have same label with y hat. Some of them may not, right? So the uppercase is choose all the all the train data have the same y as y hat and sum them up. And the downside is the sum up of all the k training data. I'm not sure if my expression is clear enough.
I understand it. I think I understand it well. So I suggest if there anyone who does not understand the concept, you can just raise your hands and we together can explain it for you.
Yeah, so we choose k in the database. And for those we have the same label with the output of our test, it's the uppercase. And all other is denominator. Yeah.
Okay. So Xiangling, is Xiangling there?
Yeah.
Yeah. Do you understand this point?
I'm still looking into a paper. You can.
Okay. So
Yeah,
it's good that so I understand that sometimes you may not follow quickly, but once you find that it's still a chance for you to raise questions to capture the idea, you should raise the question immediately. Of course, you can just go over the videos because we're all recording it. But anyway, once you find a chance, you can catch the idea quickly. You should take this chance to ask.
So
I have a question.
Okay.
Here, k means the number of classes. Number of clusters.
It's a hyperparameter.
No, it's a hyperparameter. Just like the KNN, we use some k there. So this k is also a hyperparameter like that.
Yeah, I know, but in the KNN algorithm, k means the number of clusters you define, right?
No, actually, cluster. I'm not. I don't think it means the number of clusters. Yeah. KNN means k nearest neighbors algorithm. It means choose the nearest k one and choose the most label of them to be the label of this test data.
Okay, so Yihao, please. I will still have some questions to ask up to you.
Okay. Okay. Because if I didn't remember wrongly, the k here, the k in the KNN algorithm is the number of classes you define, the number of classes you define. And so my question here is whether we choose k as the same as the number of classes in the target.
Not necessary. Yeah.
I think this k is just tuning the. It's just a threshold parameter to choose the k neighbors.
Okay. I also have a picture for this. So it's quite straightforward. If it's the same labels got. Yeah, so if the one point is in the investing is close to all the, it's labels test data with same labels, confidence score will be high. If it's not, then the confidence will be lower. Yeah.
Yeah, I still going to raise the questions. Maybe if anyone could answer, I think Wang Chao definitely can answer. So I'm going to ask, what if we're using the exponential operation into a linear operation, or using a squared operation? What are we going to happen? So why we need to have an exponential operations here? So maybe Wang Chao, you do not answer this question first. Let me ask Yihao, can you answer these questions? Why we need an exponential here?
Just now I saw that it is called a refined Euclidean distance, right?
Basically, it is, I think, fx minus fx trend j, and
It's a Euclidean.
it is Euclidean distance. But after
Yeah.
the Euclidean distance, you would have an exponential, especially the exponential to a negative Euclidean distance. Why we need such an operation? So I think this is a very good mathematical operation there. So maybe I just raise a question here to see if anyone can grasp the idea behind it. Okay, so Wang Chao, maybe you can answer the question.
I'm not sure I'm understanding it wrong, correctly, but for this one, actually the closer the higher point. So we need, so like if the two points are close, it will give a higher weight. If two images are not close, it will give a lower weight. So, so it should be a decreasing functions.
Yeah,
so,
I think exactly the point. But I think you grasp a beginning step. But after these logics, can you go further?
Actually, it's also something. I'm not sure. Actually,
Okay,
it's
so
also something.
okay, so let me give the answer because I have already given the time to think. So the idea is that sometimes the k here is very tricky. So suppose we're choosing a larger k. Sometimes because we do not know what is the probability k is. Suppose k goes from 12 to 20. So that means it is possible that the nearest neighbor have some different classes, right? So,
Yeah.
but by right, if this giving the mathematic properties, that means the larger the Euclidean distance, the smaller the final value. Let me write it down. Let me draw a picture here. So this is suppose this is coordinates, right? So basically suppose the function of e minus x should be something like this, right? And this is 1, right? So suppose the distance, suppose you can see, suppose we choosing a distance here, and we will have such a mathematical property. We will have a discount with a larger distance, and it means that we will, despite we were choosing a k, maybe we will choose a larger k, but we still focus on its nearest neighbor.
Yeah.
Yeah, so that's a good probability. So
it's not linear.
Yeah, it's not linear. So basically, it will means that it will put more weights on its close neighbor instead of the far neighbor. So suppose you randomly pick a very large k, and maybe the one, then the half of them, half of the most distant one does not have very little effect on the final dx. Can I get my point?
Yeah.
Okay.
I think you are what you said is true. Yeah.
Okay, please go on.
Okay, so after understanding this, so this is
let me see. So Xiangling, did you get my point?
I think so.
Okay, please go on.
Okay, so that's how the confidence score is calculated. So the third question to answer is that is hypothesis always true? So it's not always true. The first is active function will introduce nonlinear, and second is what you mentioned, the input of the image may also be very different. So the author proposed 2 ways to achieve effective embeddings, so make the hypothesis more reliable. So the first it also used is called the augment the network's loss function during training, which is also a very simple idea. Yeah. And the second is using adversarial training. So the first, I'll introduce the new loss functions so also introduced. So basically, for the typical CNN task, we only have this loss. It's a cross entropy loss for the classification, right? So for this, also introduce something called pairwise distance loss in embedding space. So how the loss is actually calculated is something like this. So
I have a question here. Do we necessary to hard coding such an embedding space, because the more fitness as we ask, the more likely we influence the final training. So think about it. Suppose without an error dist, we can already classify or learn the training data well. But if we add the error dist, that means we incur more overhead during the training, right? That means the network need to conform to two property. The first property that we need to minimize the error class. The second, we need to also minimize the error dist. And for error dist, that is, I think that can be learned, but that means we are not necessarily able to fully optimize error class, right? That means we have two goals to optimize.
So you can see the alpha here. So it's actually it's a retraining process. It's more like a retraining process instead of training from the.
So that means we train error class first, right?
Yeah, it's yeah. So both adversarial training and this identity loss is not trained from scratch. So it's like to have some raw embedding phase first, and then use this, and then introduce this actual loss to refine the embedding space.
Yeah, but I'm thinking that is the idea that suppose here is x, so x1, and here is x2, right? Suppose, and let me use another color. This is x3, right? The idea is that it seems that x1 and x2 belong to the same class, but there's x3 in between, right? Yeah. So the idea is that when we have such embedding space, so in the embedding space, we want x1, x2 closer.
Yeah, correct.
But my point is that why in the real case, because you can see Xiangling and Zhengfeng, is Zhengfeng there? Zhengfeng is not there. Zhengfeng is gone, right? Zhengfeng is gone.
Oh no.
Whatever it is. So the point, Xiangling, you need to capture this point, yes. So we still can draw a boundary here, right? So we can still draw a boundary here, means that this is maybe an island in the embedding space, which is in between x1 and x2. That is still possible.
Correct. We can draw a boundary, but the idea is that but it's not. But this situation does not satisfy the hypothesis.
Yeah, the point is that suppose it is. Okay, please go on. I think we can somehow refine. We can somehow refine this metrics, because this is one published in 5 years ago, 5 or 6 years ago, right? So definitely this is a preliminary.
I think it's 2017. So it's
3 years ago. Okay, so I think I do have some idea to improve upon it, but you can finish it.
Okay, so the distance. So this L dist is calculated pairwisely. So if the two label is similar, is same, so it punish for the loss, the distance between them. So punish for too far, and if the distance, the label is not similar, so it will punish for this if they are too close. But if it's
so the P is still neighbors. The P the neighbors.
I think this P is this enumerations. Yeah. So it's all the pairwise distance.
All the pairwise distance.
Yeah, correct.
All right. So it's more like we calculate the t-SNE, right? Every pair. Suppose we have 1,000, and that suppose we have 1,000.
But this one is batchly calculated per batch, not per for whole data.
Yeah. So actually, Xiangling is training the t-SNE plus. We still do the calculate the fitness per batch, because it is unrealistic to train the whole data set. But the underlying principle is the same. Basically, suppose we have a super large memory in GPU, so we definitely feed all the data into it to do the calculation. The only restriction or limitation here is that we do not have a large memory, so we have to train it per batch, because when we sample, it's very likely that some important neighbors is missing in this batch, right?
Yeah, I agree. I
Yeah.
agree with that. So the idea is quite similar, and I also agree that the way Disney adopted is much better than this eldest, because first M is a hyperparameter and is not so so necessary.
I have a question. So what does P mean?
So it's just a numerations. You can interpret this as for each pair of ij in the. So we got I batch, right? So we can got I times I minus 1 pairs of
Divided by 2.
yeah, they divided by 2 pairs of classes. So this P means all summing them all together.
Okay. So okay.
So after, but this one idea is that after the distance is already very far, like bigger than M, it will not punish it. So if it's closer than M.
So for every pairs you compare each dimension, right?
So compare the Euclidean space distance in the embedding space.
Okay. Okay.
So that's the idea how the modified loss function is. Yeah.
Okay, Wang Chao, I have a question for you. So
Correct.
what if M here is very large?
So so it will somehow affect the original performance. Yeah, but
Yes, it definitely will influence the performance.
but
So I'm asking. You can think about it. You can think on the fly. I just raised some questions. What if the M is very large? Suppose yi is not equal to yj, and M is super large, and what is going to happen?
So it's just like you have a very weird initial value for the neural network.
You can see. So you can see the max value is here to do restriction. If xi and fj is different and they have a very large distance, so we do not punish them, right? So this is the idea.
Yeah, correct.
And what if M is very large in this case?
So we will still push the x and so I and j from apart, but I'm not sure what will the true other side effects.
Yeah, I think the basic idea, I think the base idea here is that we will punish more different. We will punish more pair.
Yeah, but actually it's still fine in high dimensional space. Anyway, the embedding is usually larger than the actual amount of class. Usually equals to the number of class, right?
I think I suggest I do not. I think I would like to not give an answer here. Maybe you can just, when you think of it, you can think about it. When you think this through, you can give the answer in the group, either in the big group or the whole group of our 17 people, or the small group in 5 people. It's fine. You can think it through it. Yeah, I just leave a question. And Xiangling, you can think about this. What if M is very large? And basically, Fan is training a Siemens model. A training a Siemens model, there is something very similar here. It's called, I just leave it here to let you think about it. I think sometimes you only learning the framework to conform the form is good. But anyway, you need to think through it, so that when you read the paper, you can criticize. You can have a critical thinking about whether this idea is successful. For now, actually, when I convey my ideas, sometimes you might follow, but it's better that you have more. If you have stronger critical thinking techniques, you can criticize my ideas. So that will be more. It will be easier for us to spark something new.
Yeah.
Okay, let's please go on.
So a suitable combination of alpha and M will lead to the better result. Yeah, that's definitely true. So, yeah. Okay, so the adversarial training. So it's not so related.
Sorry,
to the
I have
idea.
a question.
Okay, what's your question?
Here the XP1 and XP2 means the input tensors, right? Input.
Yeah, you can see the test data. Yeah,
It's embedded training data.
No. FX. So XP1 and XP2 means the input. Yeah, correct. So the each line of the batch.
No, this is a
Okay.
pair. You mean the pairwise distance in the embedding space, right?
Yeah, no. This one means embedding.
Oh, all right.
This
Yeah,
one
You calculate it
means,
here. I mean,
the-
this
the-
is,
the-
you
yeah,
calculate it
the-
here, right? I see. So
Yeah, correct.
And why here is not using the exponential of Euclidean distance? It's directly using the Euclidean distance.
So you mean why this is not exponential here, right?
Yeah.
Yeah, that's also one question. Yeah, it's a good question. I don't think I can understand. I can answer you for this for now. Yeah, there's one possible improvement for this because it will critical more when it's close, but critical less when it's far. So it can somehow reduce the. Oh, let me think. So, but it cannot solve.
Wang Chao, I think you should answer these questions because these questions is very.
Yeah, because if you so for this one, I need a positive. So this one is increasing function, right? So, but if you use exponential one as a, so it will go uncontrolled. So the gradient will be super high if the distance are far at the initial. This will cause learning be very unsuitable. Yeah.
Let me think about it. So here, I think Wang Chao, you did not answer the question in a more convincing angle. So Yihao, if I'm the one who's going to answer the question, is that we are in different situation now. In the previous slides, all the embedding space has been fixed. We are calculating a confidence value, right? Here, the problem is that the data points of the same class may be far away. So that means if we calculate the confidence score in previous slide, the assumption of calculating such confidence does not hold anymore. So here we are going to let the data points or let the sample of the same class closer. So here we cannot using such a function, such a exponential function, because here even the data points of the same class can be very, very far away. So in this case, we are not we may not using the exponential.
Yeah, because if it's you can.
Yeah, let me think about it. Is there anyone who have the other ideas?
So
if we use the exponential, that means if the two input image from the same class have their distance are too high, then the loss function will the L dist will dominate the whole loss function.
Yes, I think yes. So here the problem is that when distance is too large, it will squeeze the average. It will squeeze the average. But anyway, we can also change the one.
Why? How about this function?
Who is writing this function?
I am writing.
You're writing the function, okay.
Yeah. So how about this function?
Yeah.
It's much better than this the original one, but it's something like this.
So here is that why we need to give this discount. Why we need to have discount here? Suppose
So
why we need
make
to have
this.
why we wanted to have larger discount or put weights for the closer data. Why we need to put weights on the closer data?
Yeah, I don't think we need. Yeah.
But I think putting an exponential here is reasonable because when the distance is large, then the gradient is large. So you will pull the very large distance pairs closer, then that achieve our final goal. Is it?
Yeah, but the gradient exponential. What's the opponent for gradient vanishing? So this gradient
Exploding.
Yeah, gradient it will very easily to read gradient exploding for such yeah. Actually, I haven't seen any loss function.
Yes, how about this? How about
expansion.
I think we still need to leave some time to Zhang Cheng. Let's how about Ruofan? You just take off, record these functions. I mean, Wang Chao, you can record these questions and send it in the group. We can leave it. We can have an offline discussion. Okay.
Okay.
Please go on.
Okay, so finally, the adversarial training part. So I believe it's not so related with the idea of this paper, but using it, you use it will actually improve the results. So the idea for adversarial training is that it will perturb the input for the model for robustness. Yeah. So can search for it for if interested, but I believe it's not so related with the idea because for any models using adversarial training can increase the robustness, right? So it's
I think you should answer this question as well because when we do the adversary, suppose the idea is that I think the idea here is more like Disney. And Xiangling, you get my point? Hello, Xiangling.
You say
Yeah, the idea of the adversary training is very much like a Disney. That means
why?
from an input, right? You do a small perturbation, and its embedding space should be also similar.
Yeah.
Did I get myself clear?
correct.
Right. So still, we can see what did the Disney needs to do. It's my high dimensional vector should be when they are after we read the reduction the lower dimension, the reduced lower dimension of the same input should be still closer if their responded high dimensional vectors is closer, and vice versa. And for adversary training, it's still the same. Suppose we do a very minor training, very minor perturbations on the images, and these images is so minor that from a human point of view, you cannot see anything, just like Yizhe. Yizhe add some perturbations on the images, and the object detections cannot detect the dogs anymore, cannot detect the logo anymore, cannot detect the input anymore. So that is not correct. So that means the transformations of the neural network models lose a lot of information. So when we added the adversary trainings, the idea is still the same, that you can see after perturbation, right? So when we do the adversary sample, when we do the adversary sample tag, that means the original images have a minor mutation or have a minor change, but its label will change significantly. So this idea is definitely relevant to this paper. Wang Chao, do you get my point?
I got your point. Yeah. So what you mean is that it's also to improve the hypothesis is true. Yeah.
Yeah.
Yeah. So, but yeah. Okay. So, it's time for questions. So, any question for the previous part?
Okay. Is there anyone who have a question? Xiangling, do you have questions?
So the change of loss function you mean to you use this refined loss function and then train the model and then to calculate the confidence score,
Correct.
right?
Yeah,
Oh,
correct.
yeah. Okay. Oh, yeah. Then no.
Okay. So I have a question to throw, and maybe I can let Wang Chao, Ruofan, Xiangling to Zhengfen is gone, right?
Yeah, he's not here.
Zhengfen should send us messages before he gone. But whatever it is, so let me raise an example. So one of my intuition here that the assumptions may not necessarily true because the assumption is strong. It's very strong, right? It's very strong. Suppose it means that you need to pick k neighbors. But why do we need to pick k neighbors? We somehow may just need to, because when we have a training data, I think one neighbor is, I think it's strong enough. Suppose the data set is clean, one neighbor is supposed to be enough. This is my first point. Wang Chao, if you have a problem, you can just raise. Moreover, sometimes we can, to be even closer, to suppose here, let me write something. Suppose it's x1, right? And this is x2, right? And I suppose, and there's another label, so let's call it blues. Here is
for the first question, if we only used one label, how can we calculate such score? There's only one reference. The answer can only be confident or not confident, right?
Yes, I'm seeing this. Let me using this example. Let's say this embedding space. Suppose I have X here, right? I have X here. So in here, we may somehow that X, if we classify X is equal to red, we say this X is red. It's more reasonable than saying that the X is blue, right?
Yeah.
What if the X is here? What if X is here? Do you think it's red or blue?
So that's why. So first, if it's so for this situation, if the neural network said it's blue, the confidence score will be 1/3, right? If the neural network said it's red, the confidence will be 2/3, right? So that's why that's the meaning why it chooses k points around it to give a confidence score. So why not just choose the closest one?
The closest one would be X3, right? But we still feel that X if suppose the closest one is X, because the closest one is X3, right?
Yeah.
But we find there's two blue, two red ones here, which may still have inference. Which may still have inference, right?
Yeah.
So in this case, that means that's why we need a multiple data point here.
Yeah.
Right.
Yeah.
That's the thing. But what I'm saying that we are not we can still have a way. We can still have a way to say it's red, even if we find one. We look into one data point. The trick is here. The trick is here. The trick is here. So basically, we are infer the data point. It's actually using the data points here, but somehow the neural network models will have a generalization capability. The generalization capability means that we can generalize a data point even if the data point does not appear in the training data. So the idea is that I just think about it, but I'm not necessarily correct, is that we can use a technique called adversary, generative adversary network, GAN. I think Wang Chao should
I know.
You know GAN, right?
Yeah,
so basically, GAN is the idea to learn the distribution of the true samples, but it's also possible. There's also a variant called SGAN, or it's called or conditional GAN, CGAN or SGAN. So the CGAN is going to learn the distribution of every label. So if it's possible, suppose we have cat, dog, and maybe cow. Suppose we have 3 categories. Of course, we can learn what is the distribution of the animals, right? But of course, we can still learn the distribution of what is the image distribution for cat, what is image distribution for dogs, and what is that for cow. Suppose we can learn that. Suppose we have again to successfully learn that. So given images with Cummings, and if we predict it is cow, suppose we learn it is cow. In this case, we do not necessarily to compare all its relative, all its neighbors. There's still an idea that once we say the cow, and we let the distribution of cow, we train again to let this cow to generate another cow. Right? We can generate a vector or image of cow, or image of the cow embeddings. So basically, the GAN is going to learn there is the latent space of cow. Suppose we have a latent space cow, we can just find a data points in all the respective latent space from each label to find the closest one of the cow. Did I get myself clear?
So you are going to choose a standable, like
so let's say this way. So given this X, and it was the model predicted this call. Okay, so that's the point. And then we can see that because in the classification models we have 3 classes: it's cat, dog, and a cow, right? Okay. So basically, each model, or we can train again for each label. We can train again for each label. So and again actually represents the distribution of each label data set, or for respect data set. Suppose we have n class, we can have n GAN, and each GAN actually capture the distribution space of each class. Is that okay?
Yeah, okay.
When we have such a latent space, so the structure again is that we have a Z0. Then we will feed this 0 into autoencoders, or sorry, it's a generator, right? We see so the generator, and then the generator will actually when we train the gator, we will have a discriminators, so they're iteratively to shoot, and the goal or responsibility of the discriminator is going to see whether a given image is a real image, right? And when we have a GAN, we can still learn something from the GAN to generate an image. Suppose we learn the data set of the cat, we can synthesize a cat which has never appeared in the training data, but it still looks like a cat, right? Hello?
Yeah, I can understand.
When we train this cat, we can start with a random Z. We start a random Z so that we will have a random cat. We can generate a random cat, right?
Yeah.
The idea is that suppose this X is predicted as cow or predicted as cat. Suppose let me raise example cat. Suppose it is a real cat. So somehow we can find a Z0 which can generate a cat. It looks generate an image here, which looks very similar to this image. So based on this idea, we can use GAN to find the most similar data points in the latent space and to see how similar they are. And with the same way, we can use a GAN of cat, or use a GAN in dog. That means from all the latent space, we can generate a dog. Which is the most similar dog? What is the most similar dog which looks like this cat? If the most similar dogs is still not looks like this cat, we mean that there's a very distant idea. There's a very distant way.
Yeah, but how can you you have a standard to say the 2 images are same? Like
the measurement could be Euclidean distance, the embedding space of Euclidean distance. So yeah, by this means we get rid of the irrelevant neighbors. So when we have a K, right? So this K have assumption that so just like what I raised here, we have x1 here, we have x2 here, and we have x3 which is blue here, blue in the middle. So it means that there's a boundary. Suppose there's a boundary between x1 and x3 and x3 and x2. We have to retrain the model to make x1 and x2 closer. But I'm saying that we do not need to do, we do not necessary to do this. Based on the distributions, we can still to achieve the same goal. But if we just using one reference, it's not good enough. So we need a way to generalization, and again, the generative adversary network can help us do the generalization to taking only one reference, but the one most representative reference to judge whether the given X is closer to which representative vector.
So if we already got this this GAN model for each class, why we still need to investigate its neighbors? We can just use these encodings to judge the confidence, right?
Which encoding?
So you mentioned that like we already got three GANs for generalizing all the encodings.
Yeah.
And then after we got embedding for the test data, we feed them into these 3 different.
No, we cannot feed the embedding the data into GAN. The input again is a Z0. Z0 is a random value.
Can I classify what is the the space you mentioned previously, the latest one?
You mean the latent space?
Latent space. Yeah. What's the meaning of this?
The latent space just means that, for example, when we believe an image is a cat, so in our brain there must be a distribution of what kind of image should look like a cat, right?
Yeah.
And this kind of the latent space, it represents for what kind of the image looks like a cat or dog. And this is what GAN learned.
I think I may need to
I think maybe you can maybe you can have discuss offline if you want to recap the idea. So here the idea is that there's two ways. The first way is that when we feed this X, if we have such a GAN, we have a separate GAN for each label, giving a new X, we can first let the discriminator to say whether it is a real cat or it's a trap. So this is one measurement. The second measurement is that we have a more, when we have the GAN, we have, if we can generate we find the closed data points in the latent space, which is similar to the giving input, it will give us more explanation. Okay, so maybe I just leave my comments here, and if you are interested, we can have more offline discussion.
Yeah, but my idea, my thinking for your comment is that if we already got 3 different networks, why bother having the original network?
No, they works on different stuff.
Yeah, I know they work as well, but our goal is to improve the original model, right? If we train a different model for the same.
Our goal is that we can stop whether we need to believe the decision of a model.
The decision of the model?
You can consider, suppose it will calculate the confidence score for the decision, right? When their image, the model says is a cat or is a dog. So we have additional confidence calculation to see whether I would like to believe it. So suppose there is a cartoon cat, right, feeding to model, and the model say it is a dog. So in this case, we can either believe it or not. And when and how do we believe it or not? We're using a confidence score to calculate the decision. And the decision is that how far this input, the cartoon cat, is away from the existing training data, right? So this is the basic idea.
Yeah. But I mean that if you're using a GAN to do this, the GAN itself can be a criticized that is apart from original model. So this GAN can be using any classifier model, not even the model trained by this the model. So it can be applied to different models, right? This GAN. So this GAN itself can be a criticizer. So it does not related to the original model anymore.
Yeah. Definitely, we need an independent model to verify it. But of course, you make a better point that GAN itself may not be reliable. So this is another question.
Yeah, I mean, if we're already using a model that is independent from the original model, then the meaning is it's less meaningless to interpret the training process of the image. Because, for example, you got an input, right? And it says it's a dog, but it's actually a cat. So we already know that the input is not correct. The model is not correct by our humans.
No, we when the model makes decisions on runtime, we never know it to make a correct decision. That's why we need a confidence score. Hello?
Okay. So what I mean is that the confidence as a model is a part. I believe we need to build a model that relies on original model to give out confidence score instead of a side one that is not related to the original one. Yeah.
That is a very arguable point. So if a model makes a mistake, whether we need to believe it itself. So this is another point here. I think we need to, basically, I think we can avoid discussions here. And you can, Wang Chao, you can record a few questions because we have quite a hot debate on your presentations. And you can, you can just write review. And then for these papers, I suggest both Wang Chao and Xiangling write review for this talk. Hello?
Okay, okay.
Yeah, Xiangling. Yeah, so after discussions, we can just write it. You can, both of you can write, and suggest that you do not have discussion before you write the review. But of course, after you finish the reviews, you can send it to me and share with others to see how you judge the paper.
Okay, can.
Okay. Okay, thank you. Okay, so
actually I got a final paper, but this is already what discussed in the last week's progress. So this in fact actually can help the visualization of Tiffany. So yeah. So because the Tiffany used for larger pictures, it's impossible for Tiffany's to use the original image to do classification. It has to use the embeddings. So right. So this one make the idea of effective embeddings may help visualization of Tiffany for original paper.
But sometimes I prefer to suppose there's a class which is suppose just like what I raised example. Let me raise example. Suppose there are two kinds of dogs. One dog looks like a wolf, and one dog is like just like a pet, just like the small dogs and the low nose and less aggressive dog, and also the very strong, the wolf-like dog, and they're very strong. And we are not necessary to map this kind of two dogs in the same in a closer space. I think it will be fine that even the same, I mean the red points may not be close to each other, and but anyway the red points can be in different clusters. That'll be still fine. Okay. Yeah. Yeah. Anyway, please.
But in such case, Tiffany cannot perform a good job on that, right?
Tiffany, let me see. The Tiffany, why it cannot? Why it cannot?
Because Tiffany does not involve training process. It's only a separating process. So if embedding, so if the 2 points in embedded space is far, it's never got possibility to be close after Tiffany.
It's okay, yeah. So they can be far, but both should be red points.
What you mean is that as long as we can get a clear boundary in the final embedding, in the final output of Tiffany, it's fine. So that's what you mean.
I think so. Maybe you can see we can have two classes of data points, and one data point is a wolf-like dog.
Okay.
And the second
I understand
the second class, So that's still fine. Yeah.
Okay. So that's all for my presentation.
Okay, thanks, Wang Chao. I think it's very thorough. And we should give him a big plot. Okay, the next one. How do I get a plot here? I'm not sure in the.
No need.
Okay, I'm not sure this here. Okay, let's give it up. Let's find the function later. So Zhang Chen. Hello, Zhang Chen.
Yeah.
Yeah. So you're there, right? Okay, please.
Yeah.
Okay.
Give me like one. Is it okay? Give me 1 minute.
Okay. So, yeah, I think I do not suggest we have a rest here. Let's finish the talk soon. Finish the presentation soon. Yeah. And I think Yihao raise questions. I think Yizhe or Aaron's, you can raise questions, and Zhang, if you are interested, you can raise questions as well. Hey, Wang Chao, your computer does not have camera, right? So you are using desktop, I guess.
Okay, let's start. Okay, so the research paper that I'm presenting today is about GUI-Squatting attack. So it's about the automation of generation of Android phishing apps. And here are the background of the research. So as we all know, humans heavily depend on smartphones nowadays, even to access things like, for example, your bank accounts and stuff like this. So, so traditional phishing involves sending malicious links to like your email or SMS, and the user has to click on it, then it will redirect it to the actual phishing websites. Then based on whatever you key in the phishing website, you will capture your essential information. So the effectiveness of this phishing attacks is reduced. Those firstly because there's a greater public awareness towards such malicious websites, so people won't fall into this trap nowadays. And also there's a large amount of research to detect these phishing websites. So because like using smartphones, we have this thing called the app. And so attackers nowadays are looking into embedding these attacks directly inside the apps. So there's two ways. One is cloning the app. That means they make a clone of the existing app in the App Store, and also repackage the app and then publish it as a phishing app. So the problems of such attacks are that the attacker firstly need to have strong domain knowledge of the original app. So for example, if it's a bank app, that means you have to know how a bank app actually works, because you have to try to mimic the logic as much as possible. And also cloning is difficult because websites nowadays have dynamic loading things. For example, like your bank account it will show like how much you have in the bank, and this is actually a dynamic content. So your phishing website might not have the same authenticity as the original app. And also there may be app protection techniques such as code obfuscation. So the original app owner will definitely not want people to know the code or how they develop the app. And also there are state-of-the-art defenses that can detect repackaging and cloning. So there are two important things a successful phishing attack on apps require. So number one is called page confusion. So page confusion is basically having a very, very similar UI with the original app. And also secondly is logic deception. That means that instead of like trying to directly copy the whatever logic that the original app has, the attacker should focus more on like providing some certain logic that confuses the user. That means like the user will get puzzled by why the user will receive a response that they believe there's something wrong with the app, but the response is not suspicious. So that's logic deception. And so this paper proposes this phishing technique called PH app. So I'll just call it a phishing. I don't know how to pronounce this word.
Yeah, the FOPs.
FOPs, something. Yeah. So this attack actually maximizes both of these factors. Yeah.
But for normal phishing website, as long as the UI is going to just take over, it's going to steal the credential information like username and password. But so what is more information does these FOPs trying to steal? So when they have logic deception, right? So they have logic deceptions. So it means it involved multiple steps to steal more information. Am I right?
Okay. Based on this research paper, actually they only steal the password, username and password. Because later I will tell you why. Because they only need the login page. They only so-called copy the login page. So
they copy the login page. Once the user inputs the username and password is that's all, right?
Yeah, that's all.
So,
that's the
so
only thing.
Why they need the logical deception?
Logic deception just means like the response that they receive from the backend server is like telling them that for example, okay, so the phishing app does is when you click the login button, the backend will throw a response saying like, oh, wrong username or password, or like server is down, or your network is unstable or something like that. So it will prevent the user from actually logging in. So, but the response like thrown to the
but the problem is that once the user have inputted the username and the password, the goal has been achieved, right?
Correct. But at the same time, you shouldn't let the user notice that they have been cheated. So you definitely cannot let the user actually log in because
I'm not
correct.
That's not correct website.
Correct.
But why does not the user cannot be aware of they are cheated? No, because they has already been cheated. Just like I just steal your money, And suppose I live in Malaysia or live in Indonesia. I have already taken a username and password. What are you gonna do?
Definitely, like, because if let's say you download this app from the App Store and it's a phishing website, and you realize immediately that you have been cheated, then obviously the effectiveness of the app to scam more people decreases, because you're probably likely to go and report the app or something. But if let's say the app is such that it cheated you, but you didn't realize that you have been cheated and you just simply quit, like you just stop using it, there might be a chance that you can cheat more people. I guess that's
that somehow makes sense.
Yeah.
But this is for Android apps. But if we go for website, the hackers or the phishers usually will set millions of the, if not millions, but they definitely have thousands of 10,000 website. Once one website is gone, just let it gone, because they have the rest abundant number of the abundant websites which are still there to cheating.
Okay.
Okay, please go on.
Okay.
So basically, idea that this paper want to claim their contribution, that they can also generate the logical deception, right?
Yeah.
So, but anyway, I think it is. Of course, when we write the paper, we need to detect the plausible overclaim of this paper. So I think the major contribution lies in they can derive a page which is similar in UI, but because they can generate, given that they can generate UI, it does not take much effort to generate some logical deception. But basically, this logical deception, I think it may not be it's not a very strong point. It's not a very strong point. Okay, please.
Yeah, okay, so the Android GUI framework actually has a lot of pre-built components that the user can easily use to create their own app. So for example, they have the layout components such as linear layout. I think it's to stack the components together, and also the actual components such as button or edit text. So edit text, a button is just a button. Edit text is like a place where you can type in stuff. Yeah, and so the GUI framework does not fully consider the security issues, because apparently there's a way to monitor the overall state change in the GUI through a shared memory in the, so basically there's a way to for example, you are using a third-party app, you can actually track the UI changes in a specific of another app. Yeah, and the UI apps are rendered by static XML. So if the attackers can extract the components, they can easily generate the GUI code themselves, because XML is like a tree hierarchy, right? So it's like it's a bit like HTML, where you have components nested inside another component. So it's actually quite easy to generate it. Yeah. So this is the overview of the FAPs. So it only requires the login page. So as we discussed just now, it just needs the login page. So it just tries to steal people's username and password. And there's no requirement of domain knowledge and existing attacking techniques. Okay, this one I may be able to explain a bit later when I explain the process. So and it's automatically generated at a very fast rate, so you can conduct a wide range of attacks, and also controls every pixel of the screen, because the phishing technique actually generates the phishing the UI ourselves. Okay, so this is the approach. So there are mainly 3 phases: phase 1, phase 2, phase 3. So this one I will start explaining. So before phase 1 even starts, actually,
will you please have an overview of these phases?
Sorry?
Would you have an overview?
Overview. Okay, so overview. So in layman terms, is firstly like you need to have an original app. So you try to extract the important features from the app in a login page. So important features are such as like the text box where you key in your username and password, the submit button, but then some other things like the forget password button and stuff like this. So those are the key components. those components are extracted and they are put in a CNN classification. So they're classified such that classified based on what they are. So they can be a text box, they can be a button, blah, blah, blah. So once they are classified, then it moves on to phase 2, GUI code generation.
How does it classify? So what is classes? How many classes are there?
Correct. That one I will explain later, like in the how.
So would you please give a few samples? So the CNN classification means that it's the input is the image, right? So it should be supposed to login image, whatever it is. So it's
okay. The thing that is classified is actually the component. So a component just means like a text box or a button that is captured within the login page.
I see.
Yeah. Okay. So these components are classified, and then based on the classification, so you now know that this area is a text box, this area is a button. Then you generate the GUI code in your own phishing app. And then phase 3 is involving the deception code. Deception code is when for example, you press the submit button, the information in the phishing web should be stolen to your own backend server. And also it should generate a response to the user such that it will make them seem like make them seem normal, so that they won't be alerted to the actual cheating by the app. Yeah, so those are the 3 phases. So because we use CNN classification, so before phase 1,
previous slides, I have some questions. So basically, I have some confusion about the classified component. IC, what does I means?
Okay, IC just means interactive components.
Okay, the interactive component. So is there in phase 2 from the arrow from phase 1 to phase 2? That means that when it detects some interactive components, it's going to recompose those components for a newer page.
We will generate our own page.
Yeah, they were going to generate our page. So what is the relation of classified button or text box to generate a new GUI?
So basically how they generate the thing is they are not gonna generate every single component of the original app. So for example, some things like your logos, your background pictures, all those things won't affect your login logic. So those things will be direct. So they will use they will just stick the whole background into the app's background. And then they will generate only the components that affect the logic, such as the text box and the button. So essentially it's like a background, it's like your phishing app is like your phishing app's login page will just be a background of the original app, as well as these specific components. So you only generate the components that are classified. Yeah. So this is good because firstly the UI doesn't change because you're simply just taking the original, like most of the original UI. Yeah, and then you just generate the components that are essential to your login. Yeah. Okay, yeah. So because of the CNN, we first have to train a model. So they actually define 6 components. So checkbox is just when you click it, you tick the box, and you click again, you untick it. So checkbox is 1. Image button is just an image that when you press, it acts like an image. It acts like a button. So edit text I've explained just now is just a box where you type in your username and password. A button is just a button. A text field is just a text, but like a text on the screen. And also others. Others just means like a toggle button. Toggle button just means you click, it's lighted up. Then you click again, it's toggled to the other side. Yeah, and image. So the others components are not really essential in the creation of the app. So it is classified as others. So these are the 6 components. So how they train the model is they actually extract these components from existing login pages of a lot of apps. So how they do the extraction is they use things like OCR. So for example, like your button, like usually on the button they have like login, submit, or whatever. So they use OCR to actually extract these features, and then I think obviously they use like a bit of like manual means to check through like whether it's actually the feature that they want, the components that they want. So this graph shows the amount of components they actually extracted for their to train their model. So as you can see, like yeah, there's a lot of each feature. Yeah, and
So this all component appear. This all the component appearing in the login page.
correct. Yeah,
I see.
yeah, for a lot of login pages. Yeah, and then they train the components using CNN. So the thing they use to train is based on the components color histogram. So like how the color, because like for example, like usually like the username and password text boxes are usually like probably like white in background, and usually the submit button is in like a is colored lah, for example like blue color or something. Yeah, so they capture the color histogram, and also they extracted the HU moments feature. So this one I think is related to the intensity of the background. The second part, yeah. And then they concatenate these two features to use it as the input for the particular component. Yeah. Okay, and yeah, so this is how they train the CNN. So now once you have the CNN model, once you put in a new component, you can actually classify it as one of the 6 components.
Hello.
Yeah.
I have a question. So for CNN, the input are the feature vectors, not an image.
Yeah. The feature vectors based on these things are like the color histogram and stuff like this. Yeah.
There is one-dimensional, not two-dimensional. Then how do you use CNN?
I believe it's 2-dimensional, right? It's I believe this is 2-dimensional, right? The histogram.
I think that hello.
Yeah.
Yeah, the color histogram basically should be 1 dimension, right? So histogram is just it's a feature vector to mean what color appears how many times, right? Or how many pixels is in red, how many pixels in blue, something like that. So why it is a 2-dimensional features?
Okay, this part I'm not too sure. I have to revisit the part. Yeah.
Oh, somehow it means that their approach is not the real CNN. I'm not sure. I'm not sure. Yes, please go on.
Okay, so yeah, we assume that it has been trained. So then it actually starts the actual phase 1. So so the first part of phase 1 is a component extraction, which means you are trying to extract these components from the like given an original app. Yeah, and these are the steps. So this is the original UI. And then they do a canny edge detection just to get out all the edges. So all the edges will be as you can see here will be detected. And then because like as you can see, there are words in the login page. So these words are actually part of one component instead of like being their own individual components. So actually they use this method called the edge dilation to actually merge the adjacent elements that are very close to each other. So as you can see, the words become one component. Yeah, and then because like when they train their model, like they use like rectangular, so they box everything using a rectangle. So they will try to extract these features by rectangular shapes. So then they use this method called a contour extraction to box these components together. Yeah. Okay. Yeah. So this is how they extract each of these components from the original login page. And then
Hello,
yeah.
Zhang, I feel it's very weird because just like HTML page, the web page should so giving how many widgets, how many components are in a page can be instrumented So I'm not sure you understand the word instrumentation. So just when you're developing an Android app, so each widget can be well corresponded. You can see how many widgets are in the screenshot. That's all. You can just check the program to understand. So why bother to do so detailed image analysis?
You mean like if you have the original?
Yeah, the goal here is that you're going to extract the component, right?
Yeah.
So the point is that you're taking the input of image. So definitely you need to go through step A, B, C, D to get the contours or get where the component. But the point is that just like images or it's not just image. It is rendered apps. So basically, you can just instrument the detailed code to find which widget is there, and we definitely know the position and the shape of the widget.
I believe this, based on what you say, is you have to have access to the original code that generates the UI, right?
Yeah, because all the APK file can be downloaded. You can run this APK in your emulator, in the Android emulator, and you have everything.
I believe like that their approach is through like a general approach where you just need an image of the original app and you can simply generate it yourself. So it's an approach based on computer vision where simply an image, it just utilizes the image. If not like,
yeah,
if you just
but if I'm going to do this, I would like to go through the APK files, because APK file it's actually we can generate as many as those screenshots by running Android apps on the emulator. I can keep it running on it, and I can have a lot of screenshots, and I can also know the positions and the shapes of every component. That will be very straightforward. Why not using this way?
Okay, how does the APK work? Is it like as long as you give them an image, it can sort of like give you the code for the components?
No, you run the whole APK files on the emulator, just like run the whole apps on your mobile.
Okay.
So when you go through the mobiles, when you click because it's a login page, right? So usually as long as I open the apps and the whole login page can be rendered.
Oh, okay, I get what you mean.
Yeah, but the problem is that we do not need to run on my mobile apps. We can just run it on the emulator or virtual machine, and we can get all the information. Why bother to use this? Because they raise a good example. But in many cases, computer vision have some false positives and a false negative.
So you mean like I mean this APK thing, it can detect any app that runs on it, right?
Yeah.
Like, is there a way like the original app can actually block it from
because the original apps have to let the user to log in, right? And they are only interested in the login page. Okay,
yeah. So so it generates the UI code, right?
Yeah.
Okay, I think that's a good point, and I believe they didn't really explain about that in their paper.
Yeah, I think it's very weird why they're using this computer vision technique. Yeah, I think when running the paper, I think my suggestion is more straightforward. It's more straightforward suggestions.
Okay. Yeah. I've thought of it like right now of one possible reason is that because like they said, they only want the very, very essential interactive components. So actually at the last part, they actually gave a table where they show like how many ICs, which represent interactive components, they actually extracted and built in the phishing app. Actually, it's around less than 10 for each app only. So I think the reason is because they only extracted the key features.
I think my suggestion still have advantage is that we do not need to CNN to recognize which component is a button or which component is edit text. Because if we run it on the emulators, definitely we know what component they are they're using in each login page, right? So I think their approach is a little bit weird. They just go a very, very long and unnecessary trajectory to achieve a very straightforward goal. Okay, please go on.
Yeah, and so you have these components right now, and they will classify these components. So output will be a 6-dimensional vector which represents the classification score for each of the 6 components. So the higher score just represents the classification. And then it moves on to phase 2. So now you have the classifications for each of the components. So some of it may be text box, some of it may be buttons, blah, blah, blah. And so they will actually have to generate the code. So like I've said just now, actually how they did was they actually put the original UI screen as a static background in the phishing app. So this will ensure that the similarity in terms of visually and pixel-wise, it's actually very, very similar. So the reason it, like I said, I explained just now, is because like features that are not the key components, actually they can just be simply replicated, and you do not have to actually generate it yourself.
Yeah, I think it's a more straightforward way to do this, that you just copy and paste the original apps and remove the rest. It just keeps the remove. But anyway, there's a need an automatic way to identify what kind of function or what kind of UI should be remains, right? So you then you repackage the original apps. That will be more easier than what they do, but we can retrieve the same goal.
So you mean like
right? The APK files.
Yeah. So you mean you simply just copy the entire code, is it?
Yeah, copy the entire code.
Then change the logic of certain components.
Yeah, yeah.
I mean, if it was that easy, then
yeah, I understand some APK files, but you know, Android code are all Java code. It's all Java code, and I think when it's running, it's using intermediate presentation code called the Smiley. It's using a presentation called a Smiley code. When using Smiley code, they might do this. I just feel that they are. I just feel that this approach is unnecessarily complicated.
Okay, might there be a possible situation where that, because I read, of course later I will actually like, okay, so I'll skip to the back part first, because there's a part where it says so there's this anti-phishing technique called the Droid Ego. So what it does is actually, because Android components are in the XML format, which is like in a tree layout. So actually this phishing technique actually tries to detect phishing app by looking for similarities in the layout. So for example, like if your button is within another bigger component and so on and so forth, and if your layout is somewhat similar to the original one, they might actually flag your app as a phishing app. That means like you cannot simply just take the original code and just use it as your own. I think is this a possible reason why they have to generate the code themselves?
If I'm going to attack this, if I'm a reviewer, I'm going to review the papers. I think the most straightforward way is that you can remove the rest of the tree, only keeping the root layout, right?
The root layout.
The bars.
Okay.
Okay. This layout is for the same image, right?
This layout, yes, correct, is for the same image. So what this means is so A is the original app, B is an app where you just simply take the same layout and let's say you remove a checkbox. Because like for example, you have to add your own deception logic into it. So certain like 1 or 2 features you actually have to remove it because it will affect your logic. Yeah. So this one C represents our app generated using this logic, our own logic. Yeah. So yeah, this is.
Yeah. Okay. So maybe this is a valid point. But my point is that once we detect, when we do the training for the CNN classifications, basically we are, basically we can just get all the, so once we run the emulators, we can all the details without CNN model. Definitely we do not need to CNN models, right? We do not need CNN model there. Okay, please go on, please go on. And I think there's quite a few slides. Can we finish this within 20 minutes?
Okay, sure. Yeah, and yeah, so how they generate is they use the original UI screen as the static background, and then they add the iterative components using the code. Yeah, that's how they generate it. And this is the algorithm. So this, okay, so the algorithm is just like what I've explained just now. So actually it has two types of code. One is the UI code. So as you can see, one of it is the UI code. And one of it is the deception code. So phase 2, they only generate the UI code. So yeah, deception code is generated in phase 3. So okay, one thing I forgot to explain just now is because the components, they have certain height and width and the position in the original app. So when they actually extract the components, right, they actually have to keep in record the positions and height and width of the component as well. So this will just be kept in the like separate place where they can, when they regenerate the thing, they can use it. So they don't just extract it, they also extract their attributes. Yeah, okay, so that's how they do it. So once they generate based on the classification as well as their attributes. Yeah, and phase 3 is generating the deception code. So deception code just means, like I explained just now, so what the main deception code they are generating is when the person clicks the submit button. So when the person clicks the submit button, they will definitely not allow the guy to log in because there's no website to log in into. And then they would simply throw a response to the user. So these are the 10, 1, 2, 3, 4, 5, 6, 7, 8. There are 10 responses that they have surveyed through their using login, looking at login methods like on the website, and they realize that there are 10 common responses they are given to the user when they couldn't log in. So the most prominent one is definitely wrong username or password. And also there are certain other responses such as like crash or server failed, or please update your app, or update your Google service and network unavailable, and so on and so forth. So these are the common responses they are given to the user. So they will simply randomly take, I believe they randomly took one of it and returned as a response to the user. So this is how they generate the responses. So there are also other small features such as like when you click on the forget password button. So those actually, is there exception? Okay, yeah. So here I'll explain. Yeah. So the different components will have different deception code. So only the ICs that are directly involved in the logic will have the actual deception code. So this means like so the edit text for filling in username and password and button for logic will button for login will have the actual like genuine deception code, such as deception messages such as like for example, when you key in your like when you click the submit button, it must be a genuine response.
Okay, please go on.
Okay, so this one is sorry, I don't know why there's a repeated slide. Okay, yeah, so this is like the image of the like generating like showing the deception code to showing the deception message to the user. Yeah. Okay, yeah, so that's mainly the three phases of generating the phishing app. So that concludes that
Okay.
part.
So I'm interested to see how they do the experiment. I think their
Okay.
approach is quite straightforward, and basically there's not much technical. I think their contribution is not. So I think they published quite a well-known journal, right? So let's keep going on.
Yeah, okay, so for experiments, they actually had two parts. One part is the technical experiment where they compare the actual technical information such as similarity and stuff like this, and the classification accuracies and so on and so forth. And the second part is actually they actually ask humans to test it, to test whether they can actually spot the phishing app from the original app. So the first part is, so they chose 50 top financial and social apps. Financial apps are like your bank apps, like your DBS. Social apps are just like Facebook, Instagram, those kind of things. Yeah. So for each of these apps, they actually generate a corresponding phishing app. So in total, you have 100 apps. Yeah. So the first experiment they did was to compare the UI similarity. So they use the mean absolute error and mean squared error based on the pixel values of both apps, and then they compare it. And actually here are the results. So these are the finance apps. So as you can see, like most of the pixel similarities are close to 100%. And for the social apps, is the same. And I think this one is, okay, so when they actually did this comparison, actually I sort of like thought whether it's actually a useful comparison or, because like based on how they generate the app, they actually simply copied the UI background from the original app. So obviously
I think 90% of the pixel are contributed by the copy the
correct, because like
background,
most of the login page are actually non-essential. So actually they don't even touch the UI of those parts. So it's definitely gonna be, so the only different parts will
So
be
your point that this paper should be rejected instead of accepted.
no, I'm just saying like this comparison might not be a very like strong indicator that the app
It
is
look like, right? They have to use a human. They have to use like humans anyway.
correct. Yeah.
I think let's go through the details. I think they have a good view. I suggest Ruofan and you to write short comments and reviews. I think based on these points, you should practice your critical thinking. So the one introduced by Wang Chao and maybe Xiangling still want to write a review. Maybe in general we can see its limitations. Do have the limitations? But basically, for reviews, Wang Chao is gone. But Ruofan, Xiangling, and you. So I suggested that I encourage you start writing the review. Right, writing the review in a more critical way, to think about what this paper is missing, and you can write the paper on that. So that will be more. Of course, it is also always easy to say this one is good, this one complement to. It's always easier to complement a paper than to raise some potential problems with that. Right.
Yeah.
So I think Sun author is my friend. Especially the third one. The third author is my friend, but of course we can. But anyway, we do not need to take care. I think he does not care about my YouTube channel. So whatever it is, you can just leave the comments there.
Sure. Yeah. Yeah, and so this is the first part. Second experiment is to test the classifier, the CNN classifier. So they actually test it with some other machine learning techniques. So some of it are like the basic techniques like your KNN, your decision trees, the naive Bayes. And also they tested it with like logistic regression and linear discriminant analysis and SVM.
This does not make sense at all. So
yeah, so obviously like, because like CNN is definitely like more advanced than the rest, and they got like a score that definitely
Okay,
favors.
let's keep going. Let's keep going this, and I think it gives you more bullets to make the criticism.
Correct. Yeah. So then they also compare it with other existing GUI code generation tools. So there are two of it. One is pixel to code and one is UI to code. Yeah, so they claim that these two are state of the art, like used by a lot of people on the around the world. And they did like so as you can see, like our phishing app is at the top where it's almost 100% similar. Whereas for those two techniques, they are actually like they're on average like probably like
They're using pixel to pixel similarity, right?
yeah, pixel to it's the same comparison as the first part.
Yeah, I think the experiment they will have some problems. Do you have some problems? Whatever, please go on. The one of the comments is that the pixel level similarity somehow does not completely convey the semantics level. So sometimes even the pixel level looks different, but from the semantic level, it is still very cheating. Is that still possible?
Yeah, so this is actually so this is the original, A is the original app, B is the app that generated.
Yeah, the major that copy paste the background, right? The major.
Yeah, correct. So it's only like, as you can see, only the buttons are changed. Yeah, and then these two are generated by the so-called state-of-the-art existing technology. So as you can see, it's actually quite different. Yeah.
Keep going on.
And then they also tested it against existing anti-phishing techniques. So the first one I've explained just now is the Droid Ego. So because they simply generated their own layout. So actually this anti-phishing techniques is not very effective against the phishing app.
Okay, keep going on.
Yeah. So another one is this one I'm not too sure how they conclude that this one is not effective, because like apparently they said like for this anti-phishing technique to work, it actually has to allow the picture, the screenshot to be taken within the app, and then it actually prohibits such a thing. So yeah, this one I can't really explain why this point. And personalized indicator, I think it just means on the actual app where you actually open the app, you actually give you a message from a trusted indicator.
I think they're using some tricks, by pausing the detection.
Correct, yeah.
Okay, please go on.
Yeah, and
they do a lot of experiment. They have a manual work like that.
Then then this one, window guard, is just like just trying to detect like window overlay. So I think window overlay just means like, let's say you open the actual bank app. The phishing app might just be a existing app that opens beside your actual app, and then based on what you type in the actual app, you actually try to steal it. But because our existing our phishing app is a separate entity with regards to the original app, so it doesn't use window overlay or task hijacking to actually try to steal information from the actual app.
Okay, please go on. So actually, they just feel that they somehow compare oranges and apples, something like that. Okay, please go on.
Yeah, and then move on to the second part of the experiment, which is human tests. So they recruited people to test.
How many participants are they involved?
Participants, let me see. Participants, I forgot the number. Yeah.
Maybe about around 20. How about maybe around?
It's probably more than 20.
10, right, or 5.
It's definitely more. I believe it's they recruited
5 friends.
Conclusive.
Right.
Yeah. Then they ask them. They give them all 160 apps
with the original and the actual, the original and the phishing one. Then they ask them, they give them the steps to open it up and type in their username and password.
Okay,
so,
okay,
so,
and quickly go through go through these slides. Yeah.
so some things that they asked was whether they feel that these responses were weird. So they only found like 27 out of the 80 phishing apps to have people telling them that the responses are significantly weird. So most of it are, they believe the responses are normal and don't look suspicious.
Okay. Okay.
Yeah.
Keep going on. Yeah.
And then it becomes then the visual similarity, obviously the score will be very high. So it's out of 5. So obviously, like from a human eye, from a human perspective, it's definitely very similar.
And definitely copy paste the background.
Yeah. Like, yeah, it's definitely from a human eye, it's definitely similar. And the third one is about whether these participants can actually identify whether I can identify it's a phishing app from the original one. So the question is, do you think this is a phishing app when given an actual phishing app? So true positive just means they actually managed to detect that it's actually a phishing app. So as you can see, it's only around half compared to that they cannot detect. So half of the phishing apps they can detect, half of it cannot detect. And then true negative just means it's an original app, but they detect it as a
okay.
Identify it as
Well, Zhang,
phishing.
I think
Yeah.
I think you have enough content to write the review and the raw file as well. Okay, let's go to the conclusion.
Yeah. Okay.
Your conclusion is that this approach has a lot of limitations.
Yeah. Actually, these limitations are cited by them.
Okay.
So the conclusion is, I think the whole process is actually quite clear. I don't really have to summarize once again because the steps are quite clear. So I'll just talk about some of the limitations that they talk about. So so they actually talk about the font, some special fonts that they are not able to mimic in the generation of the code. So there will be a huge visual difference if the real app uses a special font. Yeah, and then because like they capture they only copy the background, but for the components they actually try to just use a generic color to represent the background. So if the essential components originally have colorful images as their background, they also cannot replicate those things.
They should copy everything, right? So they
Yeah.
copy everything.
So just means that they cannot really copy the things that are essential. And yeah, and then they also talk about the resolution issue where they actually have to enlarge their components to fit, because they simply just take one login page from any of any mobile device. So
Okay.
so the resolution needs to be
Yeah, I think that definitely is also, this
Yeah.
is not a very fundamental, it's not a fundamental approach, but basically for this approach, I think they do have some technical alternatives, which may work even better. Yeah. So basically, you can just refer. So I think these papers, maybe that's not what I intend to let you. I was frankly, I expected more technical novelties from these papers because it's definitely published on a very well-known venue. But anyway, I think it's a good way to practice critical writing. So anyway, Xiangling, Ruofan, and Zhang Cheng, you will be and Xiangling and Ruofan will be PhD. So definitely the technical writings, especially critical writings, is very important for both of you. And Zhang Cheng, you have decided a future, but it's good that you assess the overall papers. So when writing the review for the papers will make you feel more equivalent to the authors instead of reading their papers. So when you're reading the papers of their papers, you will feel that they maybe in upper levels you look up. But when you begin to write the review for these papers, you begin to look down. So as soon as you look down those research work, you yourself will become a more competitive researcher yourself. Yeah. Okay. So I think there's no other questions for this paper.
Okay.
Yeah. Okay. Okay, so in this case, let's call it a day.
Okay.
Okay,
Thank you.
and thank you for everyone's attendance. Bye.
Bye.